For this lab, you're going to be looking at how does the radius of a spinning object, you're going to use a spinning stopper, affect the velocity that needs to be spun at under a constant centripetal acceleration. Now your constant centripetal acceleration, centripetal force in this case, is going to be provided by a 200-gram mass or some other mass along those lines that you're going to keep the same the entire time. If you're picking a different mass besides 200, recommendation, don't go all the way up to a kilogram. Don't go less than 100. Whenever you're within those ranges, you can probably spin it fast enough, slow enough to make this work. Beyond that, it's going to be really, really hard. Even half a kilogram is going to become very, very difficult. 200, 300, 400 grams, somewhere in there is a nice mass to keep constant at the bottom to keep your centripetal force constant. So you're looking at what happens if I increase the radius that I spin the stopper at, what's going to happen to the velocity of the stopper. And so the way you'll do that is you'll have a tube with a string that passes freely through it. Notice how I'm only holding onto the tube. I'm not letting anything else touch that. And I'm spinning the stopper around over my head there. Let's actually talk about how to measure the radius here. Now, to measure the radius, you'll have a meter stick, like over here. It's your independent variable radius, so you're setting it. You can put the stopper out, put it next to the meter stick, pick whatever radius you want. For example, here I have this going all the way to the 50 centimeter mark, with the stopper right there. Use a binder clip maybe to mark it. Now I'm going to clip the binder clip down on the bottom part of the string. Notice though, whenever I do that, I don't clip it so that the binder clip touches the plastic tube there. That way, I know that approximately this distance right here is going to be 50 centimeters. Once again, notice how the plastic tube did not touch the binder clip, it's just barely below. That way, whenever I hang my mass on the other side, on the bottom part of it, I can get this thing going over my head, and I can keep it at approximately the radius that I chose. Independent variables, something you set. Now, to get it going, I highly recommend hold on to the string at the bottom, then start swinging it over your head. As you saw, whenever you start to feel the forces balance out, that's whenever you can let go of it on the bottom. Binder clip staying about the same distance from the bottom of the tube, indicating the radius of this spinning stopper here is about 50 centimeters. Plus or minus probably here for your uncertainty, because I have a little bit of play in this, probably plus or minus, at least for me, the distance that I notice I'm sinking up and down, probably about plus or minus 2 centimeters, maybe plus or minus 3 centimeters, probably plus or minus 2 centimeters. So I have it spinning around. I can set my radius. How do you measure the velocity? Now, the velocity is going to be the distance divided by the time. So the distance that it goes around once is the circumference of a circle, 2 pi r. I just need to know the time, and the time is what you're going to collect as your raw variable here. For your raw data. Now, as I'm spinning it around, trying to time how long it takes to go around once would be very, very difficult. Instead, time how long it takes to go around 10 times. So, have one of your lab partners, whenever you have this held about constant, and you've got a good feel for it, I've got a binder clip about where I want, time, how long it takes to go around 10 times. Maybe, for example, here, we would start 1, 2, 3, 4, 5, 6, 7, 8, 9, stop. And then you would record that time. Save yourself a little bit of time on collecting data. Don't stop spinning until you finally get all of the data done for your first independent variable value. For me right now, 50 centimeters. And so I would keep spinning because it doesn't take that much, it doesn't take that long for my partner to write down the time it takes to go around 10 times in the raw data table and then come back and time another 10 times around. So I would do that 5 times, right? 5 repetitions of that first independent variable value. Then I'd pull it down. Like you saw, I just kind of pulled the bottom of the string while holding my hand up higher and higher so that it spun down. And then I could adjust to my next chosen independent variable value. Maybe if I did 50 to start out with, maybe next one will be 40. When choosing your independent variable values, you probably don't want to go too much longer than, 0.6, 0.7 meters, would probably 60, 70 centimeters would probably be kind of the maximum that you would want to go. 50 might even be the max for some of them. Don't go smaller than 10. Divide your values in between 60 centimeters and 10 centimeters, 70 centimeters and 10 centimeters. Any smaller than that, the radius becomes so small while you're spinning it up there that it's going to be very, very difficult to try to keep everything going. Obviously, during this lab, You'll wear goggles the entire time. We don't want anybody's eyes accidentally getting knocked out. There will be a lot of different moving stoppers around. And whenever you do start to lap, you're going to spread a long ways out from each other. Other things that I want to mention to you here, things that you definitely need to keep constant in this lap. The hanging mass at the bottom, which I've already talked about. The setup, specifically the stopper at the very end, because one feature about the stopper needs to remain exactly the same as it spins around. Remember that control variables are not materials, so there's some feature about this stopper, some specific variable about the stopper you need to keep the same. And as you spin it, you want to make sure that hopefully the variables you chose will enable it where when you're spinning, you can keep the stopper spinning around completely horizontal, so at a certain angle here relative to the ground. I want to make sure that that's the same, because if I let it go too slow, for example, I need to hold on to the string. Notice how it starts to dip down, right? And whenever I get that kind of angle going on, then I have to deal with components of the tension, and I definitely do not want to have to do that. All right. So investigation: how does the radius affect the velocity while keeping the centripetal force constant? See you in lab.